Hello physics students. In this video, you're going to learn how to determine the net force on an object that's experiencing multiple electrical forces. To do that, you have to realize that the electrostatic force that we learned how to calculate 2 videos ago is a vector like any other force. And that means when you're adding multiple forces, you have to use vector addition rules. That might mean 3 possibilities that we're going to look at today. One possibility is you're adding the forces in there in the same direction, maybe like 3 newtons this way, 1 newton that way. Then we would add 3 plus 1 and you'd get 4 newtons in that direction. But another possibility is you might add 3 newtons like this and add to that 1 newton like this. And now you use the mathematical operator of minus. 3 minus 1 gives you 2 in that direction, even though you're adding, you're subtracting because they're opposite directions. And then the third possibility we're going to look at today is what happens when they're 90 degrees to each other. Then you might remember that you have to use the Pythagorean theorem to find the net force here and the tangent function to find the direction. So those are the 3 examples we're going to look at with the following charges. So here we are, Coulomb's law is a vector. Example 1, determine F net on this 1 microcoulomb charge. Before we even begin calculating, we've got to figure out the directions. So this 2 microcoulomb right here, that is going to, notice how this is positive, like charges repel. So this is going to repel this one this way. And so I can draw that force like this. And I'm going to call it F2 because it comes from the 2 millicoulombs. Now, the 24 microcoulomb over here, opposites attract. This is negative, that's positive. This negative is going to pull and attract this one here. So I draw that arrow like this. We're going to find out it's longer. And I know that because I did the calculations ahead of time. And I'm going to label that F24 because it's coming from the 24 millicoulomb. So now that I know the way the forces are, I've got to calculate them because obviously I'm going to add these. They're both in the same direction. So I begin with Coulomb's law. Oh, by the way, let me first, before I move on, I forgot, let's create a pause to allow you to copy this down. All right, so this formula, again, you do not have to memorize it. It is no longer on the back. We have moved on from the mechanics section. It is on page 4 of the reference table in the electricity section. You see right at the top there is Fe equals KQ1 Q2 over R squared. And while I'm here, the K constant is front cover of the reference table right here. You scroll and right here you see the Coulomb's constant 8.99, 10 to the 9th. We're welcome to use 9 times 10 to the 9th, which is what I'm going to do. So let's go back to the board. And 9 times 10 to the 9th, that's K. Now this 2 times 10 to the minus 3. That's because it's a millicoulomb, not a coulomb. And I won't rush up to the camera again, but front cover of the reference table in this region, you could see what milli is, and you see milli is 10 to the minus 3. So instead of the milli, I put 10 to the minus 3. I have to do that. And then this micro is also on the front cover here. You could look up the micro and you'll see it's 10 to the minus 6. So that's why you put 1, not micro, but 10 to the minus 6. Essential, otherwise you get the wrong answer, you lose points. And the 3 meters away between those 2 charges, and I get 2 newtons. All right, now, the next charge, the next force, I use the same formula, 9 times 10 to the 9th, 24, 1 microcoulomb, 6 meters. And you might be looking at that and saying, wait a minute, it's not 24, it's negative 24. I mentioned this briefly in the first video on this topic. Do not plug negative signs into this formula. If you do, it's going to mess you up. The negative is just to figure out the direction of the arrows. If I put a negative here, what I would get, and you're not going to write this down because it gives you the wrong answers, I'd get negative 6 like this. And then when I go to add those later, I'd do 2 plus a negative 6, I'd get negative 4. So I'd really be subtracting them. So the minus only makes confusion. Put just all positive numbers. Then do you add, do you subtract? That comes back from our analysis we did earlier. So let me give you a moment to copy this down. All right, moving on. So the net force, as I said, we've got to add these because they're in the same direction. So that's what I have here. The F24 plus the F6. And again, this is, I leave it positive, 6 plus 2. 8 newtons to the right is the net force. So let me create another pause to allow you to copy this down. All right, let's move on to example 2. So for me, this is going to be easy. I'm just going to go like this. Oops, wrong marker. That was easy. And then I'm going to do this. All right, there we go. New example. So, let me erase these arrows so we could start fresh in that regard. So, but you have to write it down in your notes so your notes are complete. So go ahead, take a moment, copy example 2 down. All right, now we repeat our analysis. Now we say, first let's figure out the direction of the arrows. Opposites attract. That means this -2 is going to pull the +1 to the left. So that makes this arrow go like this. Oops. And I will call that F2 again. I didn't change anything here, so opposites attract here as well. That means this negative charge over here is going to pull this positive this way. So this arrow I could have left alone. It didn't change. F24. All right, so yeah, maybe I should have created a pause here because add those, make sure those are added to your diagram. So I'll create another pause. Okay, this is the same. So you don't have to write that down because basically it's redundant. You'll be able to see in your notes. You could even put just a note, same numbers maybe over here, like something like this. So same numbers. Something like that would work. And then when we get to over here, things change a little bit. So what we can see is since that's to the right and that's to the left, now we don't plus these numbers, we subtract these two numbers. So filling in the pieces, we could say, therefore, we've got our 6 newtons and our 2 newtons. I should have said 6.0 and 2.0, but that's all right. Minus equals, and then when we do that out, we can say F net is 6 minus 2, or 4.0 newtons. That's the magnitude. And the direction is to the right again. All right. So let me create another pause to allow you to copy that last bit down. Okay, let's go on to the next example. So let's see. Example 3. All right, now this will change a bit more. Let's do maybe. Got to figure out the spacing here. And plus 1 microcoulomb is right there. And this is still 6 meters. And this is still 3 meters. That's kind of in the way. Maybe I'll go 3 meters right here. All right, so there is the situation. So what I need to do is figure out the attract, repel, the directions of the forces. This is positive and this is positive here still, right? So like charges repel. So what I would have is a downward arrow like this. That's coming from that charge here. So this is F24. And then, like charges repel. So this is going to be F from the 2. So now we see that these are 90 degrees to each other. So I can't add, I can't subtract. What I have to do is construct a parallelogram, or in this case, it comes out to be a rectangle. Like this. Remember, this is all the way back from the forces unit, the first unit we learned about. And so the net force, the object will sort of accelerate in this general direction. So I could call that F net, but I think it's a little more compact to call it R. And then I could put a theta anywhere I want. So maybe I'll put a theta right there. Okay, so I need to figure out these legs and then figure out that hypotenuse. So fortunately, I could use these same numbers. See, I'm recycling this to really kind of speed it along so we don't get bogged down too much with notes. So take a moment, copy all this down, and I'll create a pause for you to do that. All right, so you know it's the same numbers. Let's move on to the next part, determining what that resultant is. So remember that in the Regents, you always have to start with a formula, so that doesn't change. I could write c squared equals a squared plus b squared. That's the Pythagorean theorem, the formula. In my particular case, I've got the resultant, or I could put F net. And then this is going to be the 2 legs are 2 newtons and 6 newtons as I have over here. Maybe I'll stick with the color coordinating. Okay, so that's 36 plus 4, or 40, is equal to r squared. So if I take the square root of both sides, I get about 6.3 is what that resultant, or I could put F net if I want. Doesn't matter. Saying the same thing. All right. Next, force is a vector. It has a direction, so I have to find the direction. As you can see, I put a theta over here. So I could use tan theta. Tan theta equals opposite over adjacent, maybe I'll write. And I guess it'll get a little scrunched over here. So opposite will be, I'll continue over here. Opposite will be this one, which is the 6 newtons, the same as this 24. So it's 6 newtons. And the adjacent side, opposite over adjacent, the adjacent's right over here, which is the 2 newtons. And when I do that division, I get 3. So what I have to do is do the inverse tan coulombs. So theta is tan to the -1 of 3. And so theta comes out to be, if you punched it on a calculator, I believe you get 72 degrees. Okay, so there is the angle. All right, let me create a pause to allow you to copy that solution down. Okay, so Coulomb's law is a vector. That means when you have multiple of these forces, you have to first figure out from opposites attract, likes repel, which way the arrows go. Then when you actually calculate what these forces are, don't plug any minus signs in. It's only going to confuse you, because if the arrows, regardless of the charges, but if the arrows are going this way together or this way together, whatever, if they're going together, you add. If the arrows are going opposite, you subtract the numbers. And if they're going 90 degrees, you're going to use the Pythagorean theorem and the tangent function as we did. So that's Coulomb's law as a vector. Now, I just want to say one thing about the homework. So the first example, I think I have it upstairs. The first example is going to be just like this with a Pythagorean theorem. The second example has 5 charges. One here, one here, one here, one here, and one in the middle. And it's going to look more complicated. You're going to look at that and say, I never learned how to do that. I don't know how. Look carefully at the diagram. Some of those forces cancel. And that means that you don't even have to calculate them. If you could see that they cancel, ignore them, and you're going to find that the number 2 looks more complicated, but when you really look at it, it's actually simpler than number 1. Okay, it'll be easier. So that's the homework, and I hope you enjoyed Coulomb's law as a vector. I hope everything makes sense to you. I'll see you in the next physics video.